Hello and welcome to Monday night office hours. As is our usual, it is just an open forum tonight. So, as you have questions, hit me up, and I'm here to answer them to the best of my abilities. Hey there, Logan. How's it going? Let's see. The following reaction has a change in enthalpy of negative 2,510 kilojoules per mole. Determine the amount of energy released if 53 grams of CO2 are produced. Okay, and then we get a okay, awesome. I mean, not awesome that you're struggling, but I'm so glad that you brought them to office hours. We will be able to work through these things. Okay, so let's start with this guy. So a couple things. Well, first off, we're given a balanced chemical equation, which is awfully nice of the problem. So we have 2 moles of acetylene reacting with 5 moles of O2 to produce 2 moles of water and 4 moles of carbon dioxide. All right, and the other pieces of given information. So just a setup to kind of the approach that I'm taking here. So first, I want to list out my given pieces of information, and actually, I take that back. Before I talk about what's given, I actually want to zero in on what I'm trying to find. That is actually step number 1. So in this problem, sorry, we're asked to find, but find is not spelled with an E. We're asked to find the energy released. All right, we're asked to find the energy released, and so that's what we're trying to find. What we're given in this problem, we're given that 59.3 grams are produced. Of grams of CO2 are produced, and we're given the delta H for this reaction. The change in enthalpy is negative 2,510 kilojoules per mole. All right. Now, the key. So, couple things to tip us off. We're given a mass, right, of one of our products. We're also, given the delta H of this reaction. So this is a stoichiometry problem involving energy, and the key to solving any stoichiometry problem involving energy is always going to be the change in enthalpy for the reaction. Now, the first thing we want to do with any change in enthalpy that we're given when we're working a stoichiometry problem is you need to know how to incorporate this into your balanced chemical equation. And the fact that this is a negative 2,510 kilojoules per mole, that negative sign tells you that the energy here is released. In other words, energy is a product. It's produced by this reaction. Once you know that energy is released, you can take your value for delta H and write that quantity in energy on the product side of this reaction. So we could write this chemical equation in the following fashion. We've got 2 moles of C2H2 plus 5 moles of O2 produce 2 moles of H2O, 4 moles of CO2, and 2,510 kilojoules of energy. All right. When you incorporate it into the balanced chemical equation, you don't have to include the kilojoules per mole because everything in a balanced chemical equation is in a molar ratio. So that's what that per mole thing is in the given delta H. That's telling you to include it in the chemical equation. You also do not, when you include energy from your delta H in your balanced chemical equation, you always write it as a positive, because remember, positive or negative delta H just tells you which side of the reaction to put it on. If delta H is positive, energy is a reactant. If delta H is negative, then it is a product. All right, so incorporating delta H in your balanced chemical equation is crucial, all right? And here's the reason why. So we're given that we produce 59.3 grams of carbon dioxide. What this balanced chemical equation tells us, actually I'm going to open a new slide, is that for every 4 moles of CO2 produced, 2,510 kilojoules of energy is released. So once you incorporate your delta H into your balanced chemical equation, it gives us a unit conversion to go from moles of CO2 to kilojoules of energy. Our problem here is that we weren't given moles of CO2, we were given grams. So if we're going to convert to energy, before we can do that with our balanced chemical equation, we need to convert from grams of carbon dioxide to moles of carbon dioxide. All right, now carbon has an atomic mass of 12.01, oxygen is 16.00, but we have 2 of them. So the molecular mass of carbon dioxide is going to be 44.01, and that is what we use here, 44.01 grams of CO2 are in 1 mole. Now that we've converted from grams of CO2 to moles of CO2, we can convert from moles of carbon dioxide to kilojoules of energy, because our balanced chemical equation tells us that for every 4 moles of carbon dioxide that are produced, 2,510 kilojoules of energy are produced. So moles of CO2 cancel, and now we are ready to crunch our numbers. So let's see here. So we have 59.3 divided by 44.01 times 2,510 divided by 4 gives us a value of 845.506,703. All right. Now, when you look at your significant digits, our initial mass has 3. Our delta H only has 3, so our answer can only have 1, 2, 3. 5 is going to round up. So 846 kilojoules is the amount of energy released if 59.3 grams of carbon dioxide are produced in this reaction. Okay, I'm going to start logging into my textbook real quick. Oops. Yeah, totally. Totally, yeah, no. This is the kind of thing that, like, it's a very different. It's familiar in some ways, Logan, because it's stoichiometry, but learning how to use delta H adds this kind of new wrinkle that takes a little getting used to. So it's all about getting repetition in. I'm totally down to answer all of your questions. All right, Kate, let's see. You wanted to see 56 part C. Ah, interesting. Oh, this actually... Okay. Let's get a fresh slide. So this is chapter 11. Number 56, part C. Okay, let me... Okay. Let's see, when given a positive dosage. Okay, real quick. Okay, so actually, before we hit this one up, just because these will go faster. So your second question, when you go from n equals 1 to n equals 2, this is larger why is this larger than going from n equals 5 to n equals 6? The answer is because it's not, the relationship is not linear. When you look at the equation for the energy of a transition in hydrogen, it's equal to the Balmer-Rydberg constant times 1 over the initial orbit squared minus 1 over the final orbit squared. All right, this is the equation. So actually, when you look at, I'm going to rearrange this just slightly. Actually, what am I doing here? I should put this up here. So that's the Rydberg equation that gives us the energy for a transition in hydrogen. When you look at these two, so in the first case, energy is the Rydberg constant times 1 over 1 squared minus 1 over 2 squared, versus for the second transition, energy is the Rydberg constant times 1 over 5 squared minus 1 over 6 squared. So over here, the Rydberg constant over 1 over 1 minus 1 over 4. So energy here is 3/4 times the Rydberg constant. That's that transition. Over here, it'll be the Rydberg constant. Sorry, that should not be an equal sign. The Rydberg constant times 1 over 25 minus 1 over 36. Let's see here. 36 times 25, we got to do some common denominator stuff. So this will be the Rydberg constant times 36 over 900 minus 25 over 900. 36 minus 25 equals, so the energy here is 11 over 900 times the Rydberg constant. The reason why the transition from n equals 1 to n equals 2 is greater than n equals 5 to n equals 6 is simply because 3/4 is greater than 11 900ths. The mathematical relationship is not a linear one, so that's the reason there. Okay, yeah, Logan, I totally see your question. When I'm done, I'll pop over to that one, and we will get into it. Okay. So okay, that's the answer to that question. Your question about delta H, if oops. Oh, hang on. Yes. They totally are. The quantized units are not the same. The larger gaps occur closer to the nucleus, and then as you get further and further out, they get smaller and smaller and smaller. Your observation, if the delta H of a formation reaction is a positive number, then the delta H for a decomposition is negative, because these two reactions, by definition, flip reactants and products. So that will always be the case. The decomposition reaction will always have the opposite sign of the formation reaction. Okay, and now we can, sorry, that was, your first two were kind of quicker and more verbal. Now we can actually hit up 56, part C. So in each pair of compounds, pick the one with a higher boiling point, explain your reasoning. So in 56, part C, we have CO2 versus C, whoops. You are totally welcome. Versus CS2. So to assess these here, we first gotta look at their Lewis structures. Both of these molecules are linear. The structures look exactly the same, except one has oxygen, one has sulfur. Now, when you look at your electronegativities, carbon is 2.5, oxygen is 3.5. Whoops. Carbon 2.5, sulfur also 2.5. So if we're talking about the difference in electronegativity, isn't this 56C? Or am I doing the wrong one? Am I in 56? Oh, sorry. Sorry. This is 56B. My bad. Hang on. Thanks for catching me there. 56C. Okay, CO2 versus NO2. Okay, so sorry about that. Oh, no, dude, you don't have to apologize. It was my bad. It's my bad. I always find it funny when people apologize for mistakes that aren't theirs. NO2 looks like this. There's our formal charges. All right, so let's look at, so we've got 2.5 as our electronegativity for carbon, 3.5 for oxygen, nitrogen is 3.0. All right, so starting off with our change in electronegativity. For carbon dioxide, we have 3.5 minus 2.5. So we come out with an electronegativity of 1.0. 1.0. So this means that we have polar bonds. Polar bonds, but carbon and carbon dioxide is a linear molecule, which means there are only two positions on the Vesper geometry. And since we have oxygen on both positions, that means this molecule is a nonpolar molecule, because the individual vectors running along each bond cancel each other. All right, so we only have London dispersion for carbon dioxide. It doesn't have hydrogen bonding because, well, there are no H's. Now, for NO2, let's look at our difference in electronegativity. Oxygen is 3.5, nitrogen is 3.0. The difference in electronegativity here is 0.5. These bonds are polar. Now, the question is, it has polar bonds, is the molecule polar? And the answer is yes. If you look at nitrogen, there are 3 electron groups. There are 3 electron groups, right? 2 of them are atoms, but one of them is that unpaired electron. There are 3 electron groups around nitrogen. When you have polar bonds, your molecule is polar unless every position on the geometry is the same. Here, 2 of the positions are oxygen. One of them is an unpaired electron. So since they aren't 3 oxygens, they don't cancel each other out, this molecule is polar. So NO2 has London dispersion and dipole-dipole because it has a stronger intermolecular force. That means that NO2 will have a higher, what are they asking about? Boiling points? Yeah. Higher boiling point. Awesome. Awesome. I'm so glad. All right, Logan, let's take a look. Take a look at your question. Okay, so the following reaction has a change in enthalpy of... Oh, okay. The following reaction has a change in enthalpy of negative 2,500 and 10 kilojoules per mole. Determine the moles of CO2 required to release... Okay. So, let's take a look. And I think this is coming from the worksheet or the exercise. So I'm just going to change the numbers so I don't give away the answer, but I'll show you how to tackle this thing step by step. Let's see. I'm going to scoot this over a little bit. So in this problem, again, every new problem you tackle, you want to start by identifying what you're trying to find. And in this problem, let's see, they want us to determine the moles of acetylene, C2H2. All right, so we're trying to find moles of acetylene. And when we look at what we're given, we're given a delta H. So the delta H for this reaction is negative 2,510 kilojoules per mole. And we're also given an amount of energy that's released. I'm going to say 5.2 times 10 to the 7th kilojoules of energy. All right. Now again, just like in the previous example, solving this problem hinges on how on your treatment of delta H. The negative sign means that energy is released, which, as we talked about in the last example, means that this is a product. Because energy is a product of this reaction, we can write it on the product side. So, so we go plus 2,510 kilojoules. All right. Now, when you look at what we're given here, we're given a quantity of energy. We're asked to find the amount of moles and the moles of C2H2. And our balanced chemical equation tells us that 2 moles of C2H2 of acetylene produce 2,510 kilojoules of energy. So if 5.2 times 10 to the 7th kilojoules of energy are produced, to find the number of moles of acetylene that it took to produce this amount, we put kilojoules in the denominator, moles of acetylene in the numerator, and the ratio is 2 moles of acetylene for every 2,510 kilojoules of energy. You'll notice that energy units cancel. And now we're ready to crunch our numbers. So let's see, 5, 1, 5, 2, 2, 3, 4, 5, 6, 7. So 52 million times 2 divided by 2,510. It's a lot of moles. So you crunch these numbers. My calculator is giving me 41,434.2629. All right, but we are limited to 2 sig figs by our number of moles, or sorry, our amount of kilojoules. So we count off our first 2. 4 is going to round down. So our final answer will be 41,000 moles of acetylene. It takes 41,000 moles of acetylene to produce 5.2 times 10 to the 7 kilojoules of energy. So Kate, that's a great question. Presumably for a different reaction. So if you had some reaction like A plus B produces C, and you were told that the delta H for this reaction was a positive 2,510 kilojoules per mole. This positive sign means that energy is absorbed which is another way of saying that energy reacts, is a reactant. So if energy is absorbed, then we write it on the reactant side, that 2510 kilojoules. And so then this would be what you would use to solve problems if you had a positive delta H. Louie, that's awesome. That is awesome. Fire away with your next question. Okay, yes. Whenever you are using energy in a stoichiometry problem, you always use positive values. Okay, this one's going the other way. Okay, good. This will be, Logan, this will be great reinforcement. So let's take a look. The following reaction has a change in enthalpy of 58.2 kilojoules per mole. Determine the grams of energy produced if 357.9 kilojoules of energy are absorbed. Okay, and they give us a balanced chemical equation. Let's check this out. So we have, starting from dinitrogen tetroxide, and this decomposing into 2 molecules of nitrogen dioxide. All right. Now, in this problem, they want us to find determine the grams of NO2 produced. So we need to find our mass of nitrogen dioxide in grams. And we're given, in this problem, sorry, we have our family dog is, he's a Labradoodle, and he was outside going to the bathroom, but he just ran around to the other side of the house where I'm in the office on the first floor, and he just jumped up in the window, and literally my monitor is right by the window. So I was working the problem, and all of a sudden I saw this dog face. jump up. So I'm explaining my chuckle in case you're wondering. Okay, so we're trying to find grams of NO2. What we're given is, whoops, here, I'm going to slightly tweak the numbers. We're going to say that we were given 550.4 kilojoules of energy are absorbed and that our change in enthalpy for this reaction is 58.2 kilojoules per mole. Okay, now here, this is a great time, an opportunity to tie in kind of what we've been discussing on the side. Right here, because our delta H is positive, that means energy is absorbed by this reaction, by this chemical process, which means that energy is a reactant for this process. Energy is consumed, it's absorbed, it's a reactant. So we can write in 58.2 kilojoules on the, oops, I didn't mean to do it in that layer, on the reactant side. .2 kilojoules. All right, so we want to find grams of nitrogen dioxide. We're told the amount of energy that's absorbed, so we're ready to start doing some stoichiometry. Right, oops, I don't want that in blue. .4 kilojoules of energy are absorbed. We want to know the amount of NO2 produced. Now, this balanced chemical equation won't give us a conversion to go from kilojoules of energy to grams, but we can convert between kilojoules of energy and moles, because all of our unit conversions from a balanced chemical equation all have to do with moles. So here, this reaction, 58.2 kilojoules of energy produce 2 moles of NO2. Kilojoules cancel. Next, to get grams, we got to convert from moles of NO2, 2 grams. Now here, nitrogen has an atomic mass of 14.01, oxygen 16.00. But we have 2 oxygens, so it's 46.01 is the unit conversion to go from moles of NO2 to grams. Now we're ready to crunch our numbers. All right, so 550.4 times 2 divided by 58.2 times 46.01. My calculator's given me an answer of 870.23. It keeps going. Or actually, hang on. I should write this out a little further. 870.237251. Sig figs wise, our molecular weight has 4. Okay, our delta H only has 3. That's going to limit us to 1, 2, 3. 2 is going to round down. The problem with 870 is it only has 2 sig figs, so we're going to have to resort to scientific notation. 8.70 times 10 squared grams of NO2 will be our final answer with the correct number of sig figs. All right, and that is that is how you handle this problem. Huh. Let's find the moles then. So if we were to do this, just finding moles, it's actually kind of easier. Because if you only have to find your answer in moles, then you don't need the molecular mass. Oops. So, because the balanced chemical equation gives you a direct unit conversion to go from energy to moles. So we take our 550.4 times 2 divided by 58.2. And so my calculator is giving me a value of 18.914. 0893. Sig figs wise, we're still limited to 3. 1 is going to round down, so this would be 18.9 moles. Of nitrogen dioxide. Kate. All right, let's see. Yeah. Logan, that would be awesome. That'd be totally awesome. All right, Kate, let me see. Your question was, can you look at CF2Cl2's polarity? Would it be possible? Totally. Yeah, so Kate, it is not possible, and here's why. Here's why. Okay, that is a great question. Let's look at the answer. So, question. The question is this: is CF2Cl2 polar? Or is it possible for the fluorines and the chlorines to cancel? Here's why it's critical. Here's why it's critical that you can't look at the Lewis structure. You can't look at the Lewis structure. You have to look at the three-dimensional Vesper geometry to determine whether or not things are going to cancel. Because if you look at the Lewis structure for CF2Cl2, you can draw it in a way that makes it look like things will cancel. Give me one moment while I neurotically draw in all of my dots. All right. So, carbon-fluorine, polar bond, carbon-chlorine has a polar bond. And if you look at this, you might be tempted to go, well, this bond has a dipole pulling towards chlorine, but so does this one. Those look like they cancel. And then with the fluorine stuff, it's pulling this direction and this direction, right? Do they cancel? Is the question. Do these things cancel? And the answer is no. Because of three dimensions. Remember, the Lewis structure does not reflect the shape of the molecule. And this carbon right here is tetrahedral. So those bonds from the two chlorine bonds and the two fluorine bonds are not 180 degrees apart from each other. They're all 109 degrees from each other. Right? All of these bonds, are not 180 where they're canceling. They're all 109. These two are 109. These two are 109. These two are 109. Yeah. And so this is where actually Lewis structures, as cool as they are and as helpful as they are, can be deceptive. Is it's easy to draw a two-dimensional Lewis structure and look at it and think, well, these look like they should be canceling each other out. You have to look at the three-dimensional Vesper geometry. And that's why the only time you're going to get things canceling is if every position on the three-dimensional geometry is the same. If all of these were chlorines or all of these were fluorines, then you'd be pulling in all directions with equal strength. That would cancel. But if not, then it'll be polar. Totally. Logan, we are ready for your next question. Oh, the chocolate problem. I remember this guy. I don't exactly remember how it goes, but I remember reading it. Okay, so a food chemist combusts a sample of chocolate to measure the energy it contains in calories. The combustion raises the temperature of 1.5 liters of water from 19 degrees to 73 degrees. All right, so we want to see how much energy this chunk of chocolate has contains in calories. So basically, we're being asked to find the energy in calories. Oh, not capital. Released by the chocolate bar. And let's see what we're given. All right. Again, I'm just going to tweak things slightly. So we're given that we have, I'm going to say 1.0 liters of water. We're told the density of water. We're told to use 1.0 grams per milliliter. We're told that the temperature changes, that initially the initial temperature of water is, I'm going to say 21 degrees Celsius, and our final temperature, again, I'm going to tweak it slightly, was 68 degrees C. We're also given the specific heat of water is 4.184 joules per gram degrees C. All right, now one big indication. So here we're trying to find the energy in calories that is released by burning this chocolate bar. And then we're given a bunch of stuff. Now this can seem overwhelming, but there's one clutch piece of information that will tell you how you want to go about solving this problem. And that is the fact that we're given a specific heat. There's only one equation we've dealt with in this course that involves specific heat, and that is the equation Q equals MCAT. All right. And in this equation, Q is the change in thermal energy. All right, that is what we're being asked to find. So we need to use this equation to find the energy that's released, our change in energy. We're given, which is nice, our specific heat. We know that. We're not given delta T per se, but we're given enough to solve it. Delta T, our change in temperature, is equal to initial minus final. Sorry, final minus initial. Our final is 68 degrees. Our initial, 21 degrees Celsius. So our change in temperature, we can calculate, it comes out to be 47 7 degrees Celsius. So now we have our delta T. The one last thing that we got to work out is how do we deal with our mass? And if you look at what we've used, well, specific heat is just specific heat. We've used T1 and T2, so somehow our mass must be connected to our density and our volume, and that hunch will be borne out because we're given a density. Density is equal to mass over volume. Given a density, we're given a volume, so we have enough information to solve for our mass. If we multiply both sides by V, we get an expression for our mass of water is going to be equal to our density of water times our volume. And again, we have both of these. So let's go ahead and calculate our mass. Whoops. Our mass of water is equal to our density, which is 1.0 grams over milliliters. Our volume is 1.0 liters, and now we have a problem here because liters and milliliters don't cancel, so we need to do a unit conversion. Liters in the denominator, milliliters in the numerator. 1 liter is 1,000 milliliters. So now liters and milliliters all cancel. 1 times 1, or mass of water, 1 times 1 times 1,000 is 1,000 grams, but we need to remember that we are limited to 2 sig figs here, so our answer has 2 sig figs. Now that we know our mass, we can calculate the change in thermal energy here. I'm going to pop over to a new slide. So change in thermal energy is equal to the mass of water times the specific heat of water times the change in temperature. Our mass is 1,000 grams. We got to remember that we only have 2 sig figs in this number. Times the specific heat, 4.184 joules per gram degree C. Times our change in temperature, which is 47 degrees Celsius. So we have 1,000 times 4.184 times 47 is 1,096, 648. I know when you look at your units, grams cancel grams, degrees Celsius cancel degrees Celsius. We're left with joules. Now, I'm not going to round quite yet, because in this problem we were asked to find the calories. So before we round, I'm going to do our last unit conversion. 1 calorie is 4.184 joules. Joules cancel joules. And 196,648 divided by 4.184 comes out to a shocking number. This is unnervingly symmetric. 47,000 calories. I can only have 2 sig figs, but 47,000 only has 2 sig figs. So So 47,000 calories are released. When this chocolate bar is burned. Yes, totally. Logan, great catch. All right, let's see. Okay, so Kate, chapter 10, number 82 and 88. Let's see. Ah. Okay, so Kate. So let me see. You asked about chapter 10, 82, and chapter 10, 88. Okay, so first off, oops. All right, so first off, let's talk about 82, which says, draw an MO diagram for HCl. Um, so in lecture, we only covered MO diagrams for homonuclear diatomics. And part of that is because of time constraints. We had to move on before we had to hit kind of everything in the topic of molecular orbital theory. And so I'm gonna go ahead and skip this one, mostly because since we only covered homonuclear diatomic molecules, I'm not going to test you on heteronuclear diatomics. Hetero meaning different nuclei. There's a couple details that we didn't cover. A couple kind of like detailed shades of meaning that that are different when the two molecules involved are different. And so just go ahead and skip number 82. Because it's just we didn't have time to cover it in lecture, and so I won't test you on it. Let me take a look at 88. All right, let's see. So the structure of acetyl salicylic acid, which is aspirin, is shown here. How many pi bonds are present in acetyl salicylic acid? How many sigma bonds? What part of the molecule are free to rotate? What parts are rigid? Okay. Okay, so to answer this question, you need to know this. All sigma bonds experience free rotation. So sigma bonds are just constantly spinning around, rotating around nonstop. Pi bonds do not rotate because pi bonds do not rotate because rotation destroys the indirect orbital overlap rotation destroys the indirect orbital overlap that form the pi bond. So pi bonds can't rotate because in order for a pi bond to be there, you have to have those two p orbitals parallel to each other in space. So if you rotate one away, you've destroyed the pi bond. You have to keep those two parallel. So pi bonds are not free to rotate. As a result, when you look at the molecule acetyl salicylic acid, which looks like this, let's see, what else do we got? Let's see, we got some lone pairs to fill in. And we're not quite done yet. We've got another. So, when I look at this molecule, wherever I see, so when I see this sigma right here, there's free rotation. There, free rotation here, 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 also around this sigma bond, free rotation's all there. When I see this part of the molecule, this part is rigid. Mostly because in addition to having those alternating pi bonds, it's a closed loop of electrons. So it's not that ring, those 6 carbons are kind of stuck there. They can't rotate because it would destroy the pi bonds that exist between every other carbon. So that part would be rigid, and then all those other single bonds, sigma bonds hanging off of the ring would be free to rotate. All right, Logan, I'm going to go ahead and start writing up your next problem. I'm just going to tweak the values for the delta H's. So here we want to find, so they give us a reaction 5 moles of CO2 gas react with Si trisilicon tetranitride, which is a solid. This produces 3 moles of silicon monoxide gas plus 2 moles of dinitrogen monoxide gas plus what was that last thing? 5 moles of carbon monoxide gas. And they want to know what is the delta H. Oh, just need to give myself a little more space. So we want to know what the delta H of this reaction is. All right, now let's look at what they give us. So they give us a reaction with carbon monoxide, solid silicon dioxide, that's sand, that produces silicon monoxide gas and CO2 gas. All right, and the delta H for this reaction is, I'm going to scoot this over, is, okay, and I'm gonna tweak these numbers. I'm gonna say this is 320.7 kilojoules per mole. All right, next reaction, we have 8 moles of carbon dioxide reacting with trisilicon tetranitride solid, producing 3 moles of silicon monoxide gas plus, 3 moles of silicon dioxide solid plus 2 dinitrogen monoxide gas molecules. And our delta H here is going to be 583.2 kilojoules per mole. All right. Okay, so let's talk for a minute about our strategy here with this problem. Whoops. So here's our plan. Our plan is to manipulate. We want to manipulate the given reactions and add them together so that all molecules not in our goal reaction cancel out. All right, that's our strategy. We want to manipulate our given reactions so that, and then add them together so that all the molecules that aren't in our goal reaction will cancel. Now, I'm going to do a really quick review of how you manipulate reactions and the effects that has on delta H. And then we're going to apply these to this reaction, this problem that we're currently working. So here's a refresher on how to manipulate reactions and delta H. All right, first, if you have a reaction, I'm going to call this reaction 1, where you have A plus B produces C, and we have a delta H here that I'm going to call delta H1. If you exchange places with the reactants and products, so let's say we have a reaction 2, where you have a product C decomposing into A and B, the delta H for your new reaction, delta H number 2, is going to be the same value as the delta H for reaction 1, but with the opposite sign. So if you flip reactants and products, your new delta H is the same as the old delta H, just multiplied by -1. That's the first relationship. Second relationship, if you have a reaction 1, where you have A plus B going to C, and let's say we have a delta H for this reaction, that's delta H1. Let's say we have a second reaction where we multiply everything in our first reaction by a number. So it changes, so now we have 2A reacting with 2B to produce 2C. The delta H for reaction 2 is related to the delta H for reaction 1. It's actually the delta H for reaction 1 multiplied by 2. If you multiply everything in a reaction by a number, your delta H, you also multiply your delta H by that number. All right. There's one last relationship we need to cover. Let's say that you have reaction 1. This is the third and final. And this one you'll use every time. Let's say we have a reaction where A reacts with B to produce C. We've got delta H1. Let's say we have a reaction number 2, where you have C decomposing to form 2 molecules of D. We'll say this is a delta H of 2. Now let's say you add reaction 2 and reaction 1 together to get a new reaction, which we will call reaction number 3. If we add these two together, you'll notice that you have 1 mole of C on the reactant side, 1 mole of C on the product side, so these cancel, and you get A plus B producing 2D. This is reaction number 3. The delta H for reaction 3, because we got reaction 3 from adding reaction 1 and 2 together, you can get a delta H for your reaction 3 by adding the delta H from reaction 1 together with the delta H for reaction 2. All right, we're going to use these 3 manipulations in this problem to find our the delta H for this reaction. All right, so we need to look and figure out how do we need to manipulate this reaction. All right, that is really what this boils down to. Now, let's do some work. All right, I'm just making sure all these reactions are balanced. 3. Oh, hang on. there's a problem. Oh, there we go. I was like, I think I wrote something in the second reaction wrong. And I did. I'm going to need to... I'm just going to rewrite this. CO2 plus Si3N4 solid plus, oh no, producing. SiO2 solid N2O gas plus 8 CO. All right. This should be balanced. Let me just give it a once over to make sure we're okay. Silicon's okay. Nitrogen's okay. Carbon's okay. Oxygen, let's see what we got. 8, 10, 16. Okay, we're good. All right, now we're ready to figure this out. So here's how you kind of want to look at things. Let's see, I need to pick. All right, so here's our goal. Our goal reaction is up there, right? We want to have 5 moles of CO2, 1 mole of Si3N4, 3 moles of silicon monoxide, 2 moles of N2O, and 5 moles of CO. In addition, we want these on specific sides of the periodic of the chemical reaction, right? We want one, for example, we want 1 mole of silicon monoxide, of trisilicon tetranitride, this guy. 1 mole of that on the product side. So what I'm going to do is I'm going to find it, Si3N4, and check that out. There's 1 mole of Si3N4 on the product side. That's good. So, oops. So I've actually have that in place. You'll also notice that I have 2 moles of N2O on the product side. Sorry, S3N4 on the reactant side, N2O on the product side. So those two both look good. Now let's take a look at SiO. You'll notice that it's right here on the reactant side. Sorry, on the product side, which is where I want it. But I want to produce 3 moles, right? I want to produce 3 moles of this, and down here I only have 1. That means I need to take everything in this reaction and multiply it by 3, all right? When I do, I will get 3 moles of carbon monoxide gas plus 3 moles of SiO2 producing Ah, Logan, that's a great question. Let me just finish writing this reaction here. You can focus on either the products or reactant side. Reality is, you need everything to line up perfectly. So you need to have everything in your goal reaction be perfect. It needs to line up no matter what. So you can start on the reactant side, you can start on the product side. Either way, it all has to work out the same. So, it's kind of like solving a puzzle, like putting a puzzle together. Some people like to put the border of the puzzle together and then work inwards. Some people like to do the faces because those are easier. It doesn't matter which one, because no matter where you start, when you start solving your puzzle, you finish the same. You got to have everything in place. So I started looking at reactants and products. I try to find the reactants and products in the reactions that I'm looking at. And so that's kind of how I approach it. Our delta H here, we also need to multiply by 3. So, and again, remember, it's this delta H that we're multiplying by 3. So we take 320.7 times 3. So that comes out to be 962.1 kilojoules per mole. All right, now you'll notice that here we're producing 3 moles of SiO2. So when I look at my reaction, my goal reaction, I've got silicon, trisilicon tetranitride lined up. I've got silicon monoxide lined up. And I have dinitrogen monoxide added up. Let's take a look at carbon monoxide and carbon dioxide. I want to end with 5 moles of carbon monoxide on the product side, right? Over here I've got 8, but 3 of them will get canceled by carbon monoxide over here. 8 minus 5 is, 8 minus 3 is 5, so that'll actually work out fine. I want to have 5 moles of carbon dioxide on my reactant side. Over here I have 8, but I also have 3 moles of carbon monoxide on my reactant side. So if I add these two, together at this moment in time, if I add them, everything will cancel just the way we want it to. All right, so carbon monoxide. 3 moles cancel 3 of this 8, leaving me with 5. So I have 5 moles of carbon dioxide gas plus 1 mole. I don't have to write that one though. Of trisilicon tetranitride plus, now these 3 moles cancel 3 of these, leaving us with 5. So that doesn't have any left over. And you're like, wait a minute, what about this silicon dioxide? That's not in the product. Well, it actually cancels with the 3 moles of silicon dioxide on the product side as well. So we have our two reactants producing 3 moles of silicon monoxide gas plus we've got our 2 moles of dinitrogen monoxide gas plus our 5 moles of carbon monoxide gas. And now to get our delta H, we just have to add these two delta H's together. So we have 962.1 plus 583.2 gives us a delta H of 1,545.3 kilojoules per mole. Sig figs wise, we don't need to round because both of these numbers have their last significant digit in the first decimal place. So does our answer. So we're good. So that is how, this is a Hess's law problem. That is how you use Hess's law. To use given chemical equations to find the delta H of another chemical reaction. It would not be 1545 because when you're adding, you have to look at the precision of the number. So both of these numbers have their last significant digit in the first decimal place, and that's why our answer must have its last significant digit in the first decimal place as well. All right, let's see. Problem 3. All right, Jason. I'm going to switch the numbers around so I'm not giving away the answer, but all the steps in the process will will remain the same. All right. So let's see. So let's take a look at review packet 3. So we have a 15 liter metal cylinder that contains, I'm going to change these numbers, but 0.108 moles of nitrogen gas at 24.00 degrees Celsius and 0.12 atmosphere. Yeah, I'm going to go ahead and start writing this down as we go. So we're going to go, so 20 liter cylinder contains 0.056 moles of N2 gas at 24.00 degrees Celsius. And 0.100 ATM. When 1.50 moles, hang on. I wanted that to be 0.56 moles of N2. When 0.50 moles of N2 are added, the temperature increases to 74.80 degrees C. What is the pressure? What is the, I should say, the new pressure? All right. So, this one, with this problem, whenever I see initial and final conditions, I always think of the combined gas law, right? And here we're trying to find P2, right? We're trying to find the new pressure. And we're always given equations, right? P1, V1 over N1, T1 equals P2, V2 over N2, T2. And we are after P2, right? Let's look at what else we're given. So we're given a volume that doesn't change, actually, right? Our volume is 20 liters. It doesn't change at all, so that actually cancels out of this equation. We're given an initial quantity of moles, right? We're given N1 is 0.56 moles, and for N2, you'll notice this is subtle. We're told 1.5 moles of nitrogen are added. So that means N2 is equal to our initial quantity, 0.56 moles plus 1.5 moles. So we are given N1 and N2, but it's subtle. We're told that 1.5 moles are added, so N2 actually is 2.06 moles. All right, we still got it, but we had to stay on our toes. We have P1, right? Our initial pressure was, where was that? There it is, 0.100 atmospheres. Now, we're given T1 and T2, but in Celsius, we need to convert them to Kelvin before we can use the combined gas law. So we have to add 273.15 in order to convert our T1 and our T2 to Kelvin. So let's see. 24 plus 273.15 is 297.15 Kelvin, and then 74.80 plus 273.15 is 347.95 Kelvin. Now that we have our final temperatures, we can solve for our final pressure. So we're actually going to clear this all the way out. So we have P1 over N1 T1 is equal to P2 over N2 T2 we need to isolate P2 on one side of this equation, so we need to multiply both sides by N2 times T2. P2 is equal to N2 times T2 times P1 over N1 times T1. And so now we're ready to plug in our numbers. We got 2.06 moles is N2. T2 is 3 was that 347.95 Kelvin. P1 is 0.100 ATM, atmospheres, over N1, 0.56 moles, times our T1, which is 297.15 Kelvin. Now, Kelvin will cancel with Kelvin, and moles will cancel with moles, leaving us with atmospheres, which is good because we're solving for pressure. So 2.06 times 347.95 times 0.1 divided by 0.56 divided by 297.15. final pressure is, let's see, we're limited to 2 sig figs because of our quantity in moles, so this would be 0.43 atmospheres. All right. Okay. This is good. This will be, again, just really good reinforcement, for Hess's law. All right. So let's see. So we want to find the delta H for the reaction where, whoops, let's get this in black, where we have 2 moles of magnesium oxide, solid magnesium oxide, reacting with 4 moles of HCl gas, producing 2 moles of solid magnesium chloride, and H2 gas. I'm guessing. Wait a minute, hang on. Something's. Oh, that was my bad. It's not H2 gas. It's liquid H2O. Okay. There we go. So we want to know, what is this delta H? That is our whole goal. And let's see, we are given a couple of reactions. First, we got solid magnesium and HCl reacting to make magnesium chloride and H2. This reaction has a delta H of, and I'm going to change this, 393.5 kilojoules per mole. Next, we have a reaction where 2 moles of solid magnesium reacts with 1 mole of O2 gas to produce uh, 2 moles of solid magnesium oxide. This delta H is negative 1106.0. Kilojoules per mole. And finally, we've got a reaction where 2 moles of liquid water decompose into 2 moles of hydrogen gas, 1 mole of oxygen gas, and our delta H here is negative 571.6. All right. Let me just make sure all my things are balanced. But it looks pretty all right. Okay. So, let's take a look here. Okay, so we want to keep our goal reaction in mind, and I'm going to use color coding like I did before to kind of highlight everything. So we want 2 moles of solid magnesium oxide reacting with 4 moles of HCl to produce 2 moles of magnesium chloride and 2 moles of water. Now, the first thing that jumps out to me, and again, there's no like right way or wrong way, so don't get tripped up over like where's the right place to start. There's no right or wrong place per se. I tend to look for reactants or products that are only in one reaction. So, for example, you'll notice that H2 shows up in a couple of these, right? O2 shows up in a couple of these, but there's only one reaction with HCl. And that's right. Whoa. Gross. Let's knock that out, Photoshop. There we go. HCl's right here. Actually, dovetailing it, there's only one reaction with magnesium chloride as well. But you'll notice that my moles are off. I have 1 mole of magnesium chloride here, but in my goal reaction I have 2. I have 2 moles of HCl here. My goal reaction is 4. So that tells me that I need to take this reaction and multiply everything in here by 2 if I'm going to get the correct number of moles for HCl and magnesium chloride. So I'm going to multiply everything by 2. So 2 moles of Mg of solid magnesium reacting with 4 moles of HCl produce 2 moles of magnesium chloride and 2 moles of H2. The delta H here is, let's see, I need to take that 393.5 and multiply by 2. Or, in other words, this is negative 393.5 minus 393.5. So this new delta H is negative 787.0 kilojoules per mole. All right. Now, I'm going to take this thing. Whoa. No, let's not do that. Let's just, how about we move it? Now, the reason why this is awesome, this helps us because we have the correct number of moles of HCl lined up and on the right side of the reaction, and the correct number of moles of magnesium chloride. All right, so we've taken care of magnesium chloride and hydrochloric acid. We just got to line up water and magnesium oxide. So let's look at our original options. Now, here as I'm shopping my options, I'm going to zero in on magnesium oxide. You'll notice that I have 2 moles of magnesium oxide, and down here, this reaction is 2 moles of magnesium oxide, but it's on the wrong side, right? This is on the product side. I want magnesium oxide on the reactant side, so I'm going to take this reaction and I am going to flip my reactants and products. When you flip, you multiply your delta H by -1. All right, so I'm going to exchange my reactants and products. So I'm going to rewrite this as 2 moles of magnesium oxide decomposing into 2 moles of solid magnesium plus 1 mole of oxygen gas. And my delta H here is a positive 1,106.0 kilojoules per mole. All right, now when I look at what this buys me, because again, our end game here is we want to add all of our things up together. And now I have 2 moles. Whoops, hang on. There we go. Now I have 2 moles of magnesium oxide right where I want it. All right, so now it's time to go after water. I want 2 moles of water on my product side. Let's see what I have to work with. So going back to our reaction, or our reactions that we have to choose from, you'll notice here I've got 2 moles of water, right? And I want 2 moles of water, but I want 2 moles of water on the product side. This is on the reactant side. So I'm going to do another flip, which multiplies my delta H by -1. So after I flip this reaction, I'll have 2 moles of H2 gas plus 1 mole of O2, producing 2 moles of H2O. And now I take this delta H, multiply by -1, so that's 571.6 kilojoules per mole. Oops. Now when I add this, you can see that I have 2 moles of H2O right where I want it, right on the product side. So I've lined up all of my reactants and products with the correct amount of moles on the right sides, all that stuff. But now I need to make sure that my other stuff cancels, all right? We have to make sure that everything else that's not in our goal reaction cancels. And let's take a look. Well, I have 2 moles of magnesium on my reactant side, 2 moles of magnesium on my product side. These two will drop out. You'll notice that I have 2 moles of H2 on my reactant side, 2 moles of H2 on my product side. These cancel. finally, you'll notice that I have 1 mole of oxygen on my reactant side, 1 mole of oxygen on my product side. They cancel. So yes, all other reactants and products that are not in my goal reaction drop out once we add all these together, which means that we are ready to add. When we add all these together, we get 2 moles of solid magnesium oxide plus 4 moles of HCl, producing 2 moles of magnesium chloride, which is a solid, plus 2 moles of H2O. And now we're ready to calculate our delta H, because we just add these 3 delta H's together. So negative 787.0 plus 1106.0 plus 571.6 comes out to be 890.6 kilojoules per mole. Oops. Yeah, so the final calculation hang on 1 second. Okay. So the final calculation is hang on. Just rearranging some things. So the final calculation is a delta H for the first manipulated reaction plus the delta H for a second manipulated reaction plus the delta H for that third is the delta H for the reaction that we're after. And our first delta H, after we manipulated it around, was negative 787.0 kilojoules per mole plus our manipulated reaction for the second reaction was 1106.0 kilojoules per mole. Delta H for the third one was a positive 571.6. And again, I changed the numbers for my calculation. So using the numbers that you gave, your answer would be different. But for the numbers that I was using, we have negative 787.1 plus 1,106. Sorry, negative 787.0 plus 1,106.0 plus 571.6 comes out to be 890.6. Sig figs wise, all of these numbers have their last significant digit in the first decimal place. So does our answer, so we don't need to round. And our units are kilojoules per mole. Oh, Logan, I absolutely have time. You don't even have to promise. You don't have to promise that it's the last. Office hours runs till 10, so we got another 40 minutes to party. We absolutely have time for more. All right, let's take a look. Let's crack into this guy. All right. So we want to calculate the delta H for this reaction. We've got 2 moles of C10H22, which is a liquid, reacting with 31 moles of O2. This produces 20 moles of carbon dioxide and 22 moles of liquid oxygen. And we want to know what this delta H is. Oh, okay. All right, Logan. Here's some great news, and I think we're due some great news. This is way easier than what we've been doing. All right, because this is Hess's law, but a special variant. This is Hess's law using the delta H of formation. All right. And this is a much easier problem to do, and you'll see how. So the delta H of formations, you'll notice they give you 3. They give you the delta H of formation for the first one, and I'm gonna change these. I'm gonna go, it's negative 400.7 kilojoules per mole. And then they give CO2 negative 393.5 kilojoules per mole. And then water, liquid water, negative 285.8 kilojoules per mole. All right. Something to keep in mind. Each one of these delta H's, the delta H of formation is literally the energy released when 1 mole forms. All right, that is the definition for the delta H of formation. So you can calculate there we go. Sorry, it took a little while to open that. You can calculate the delta H for a reaction. Remember, delta is final minus initial. Delta is final minus initial. So the delta H of this reaction is the final state with the delta H of formations of the products, that's final, minus initial delta H of formation of all the reactants. And you'll notice we're given the delta H of the products. We're only given the delta H of delta H of formation of one of the reactants. That's because O2 is an element. And elements are the simplest form possible, so that's 0 kilojoules per mole. Anytime you're dealing with an element. So we have all the delta H of formations for our products and reactants. So that is how we're going to calculate the change in enthalpy for this reaction, because they give us the delta H's of formation. It's much easier than all that manipulation of reactions that we did previously. Now, so the delta H for this reaction is going to be equal to, now, products, right? We've got the delta H of formation for CO2 plus the delta H of formation for H2O products minus reactants. Delta H of formation for C10H22 plus delta H of formation for O2. Now there's one really common mistake to make, and this is what you got to watch out for. You'll recall that I said the delta H of formation tells you the energy released when 1 mole forms. Well, you have to ask yourself how many moles of each thing forms in this reaction. And for CO2, you're making 20 moles, so we need to multiply this by 20. For water, we make 22 moles, so we got to multiply that delta HF by 22. For C10H22, we make 2 of them, so we multiply that delta H of formation by 1. Oxygen, we consume 31 of them, but remember, oxygen's is 0 kilojoules per mole anyway, so it won't matter because that is just with 0. So our delta H of reaction is equal to 20 times delta H of formation for CO2, negative 393.5 kilojoules per mole, plus 22 times the delta H of formation for water, negative 285.8 kilojoules per mole, minus 2 times the delta H formation for C10 H22, 400.7 kilojoules per mole. Plus 0 because oxygen is an element. So, all right, now something to keep in mind when you multiply by these stoichiometric coefficients. You're going to keep the same precision because those stoichiometric coefficients are exact. So this is as if we're adding this number 20 times together. So 20 times 393.5, so that's negative 393.5. Will be negative 787, or 7,870.0 kilojoules per mole. 22 times negative 285.8. So this is minus 6,287.6 kilojoules per mole. Now, we have a double negative here. This negative times this negative is going to make a positive. So we have 400.7 times 2. So this will be plus. Oops. 801.4 kilojoules per mole. So it's not the number of sig figs, actually. We have to keep the same... we got to keep the same precision. So I'm going to open a new slide really quick. When you have the 22 times, for example, negative 285.8 kilojoules per mole. Here's what's going down. This is exact. All right, that 22 is exact. That means what we're actually doing is we're taking this and we're adding (22) times. Oops. So you're not looking at the total number of sig figs, you're looking at the decimal places. And when you go negative 285.8 minus 285.8 minus 285.8. Then you go minus 285.8. So let's see. So this is 18 more negative 285.8. And you subtract all of these from each other. The answer is negative 6,287.6. And because the precision, all of these numbers have their last sig fig in the first decimal place, our answer must have its last significant digit in the first decimal place. And it does. So you don't count 4 sig figs. You actually look at the precision of the number, the last decimal place. Because that 22 is exact, we're actually doing arithmetic here. So that's why we have 6,287.6 and 7,870.0, because our precision has to be the same as the number we start with. So that's why that works out that way. So now we take negative 7,870.0 and subtract 6,287.6, and we add 801.4, and we get negative 13,356.2 kilojoules per mole as an answer. And again, all of these numbers are precise to the first decimal place, so we have to have an answer that's precise to the first decimal place, and we do. Great question. Logan, great question. So if you have those two numbers, let's say you had, let's say you had 16 times 35.21 plus 9 times 200.9. When you did the math for the first one, so 16 times, here, let me throw some units in here just so we're clear on which numbers are measured and which numbers are not. Kilojoules per mole. There we go. Kilojoules per mole. When you go 16 times 35.21, that would be 563.36 kilojoules per mole. And you keep the same precision, so 2 decimal places. For our second number, 9 times 200.9, that's 1,808.1 kilojoules per mole. And now, precision was 1 decimal place, so you have 1 decimal place. Now when you add these two, you'd go 1,808.1 plus 563.36. So the number adds my calculator's telling me the answer is 2,371.46. But because our 1,808.1 is only precise to the first decimal place, our answer must be precise to the first decimal place. So when we'd add these two numbers together, we'd have to round that 6 up. So our final answer for this scenario would be 2,371.5 kilojoules per mole. Awesome. Oops. Dude, I'm so glad to hear that. I feel like we're making progress tonight, which is awesome. It's what office hours are for. All right, let's see. Step 3, lab setting calculations. Let me take a look. Okay, let's see. Data analysis. Okay, Lauren, quick question. I'm looking and I see a data analysis step 1, data analysis step 2. So I don't know if maybe you have a page number or maybe a little more information on what you're looking at when you see/say step 3. Okay, let's see. Oh, okay. So, Lauren, I think I'm looking at what you're asking about, just to double check. Because that says this gives the milliliters of stomach acid neutralized per gram of acid. Okay, okay. Awesome. Okay, so yes. Okay, so here's so they line up the calculation, but sometimes when they just throw um, a bunch of kind of conversion factors together, it can make it hard to understand what exactly is going on. So for this calculation, this particular step, we're looking at the milliliters of stomach acid that get neutralized by every gram of antacid. All right, so that's what this step of the calculation does. And what you do is, so you take the milliliters of neutralized HCl. So what I'm going to start by just writing what they have, and then I'm going to explain it. So just bear with me for the moment, and then we're going to unpack what this whole thing means. All right. Then they have 1 liter per 1,000 milliliters. Then they have 1,000 moles of HCl over liters. Then they have 1 liter over 0.14 moles of HCl times 1,000 milliliters per liter. All right, so let's unpack this. So the first two things are so the first two things are, this is right here. Wait, hang on. Sorry, I want to do this in a different layer. These are the milliliters of HCl. That the antacid neutralized in the experiment. All right. This is connected right here. This quantity is the molarity of HCl from the experiment. So if your data set did not use 0.1 molar HCl, you would just use whatever the molarity of HCl that you actually used. That's a little, I'm just going to bump this down. All right, so that quantity is the molarity of HCl from the experiment. Now, if you're wondering what is this guy doing here, this is simply to handle the unit conversion milliliters up here and liters here. So that's there to cancel that. And this is here to cancel this. All right? Now, this quantity, if you're like, what the heck is this thing? This is the molarity of stomach acid. See, stomach acid, so we used a concentration of HCl that was not exactly the molarity of stomach acid. So we know how many milliliters of our HCl got neutralized, but we need to use the molarity of stomach acid to convert it, because it's a different concentration, so a different volume of stomach acid will be neutralized than the volume that was neutralized in this experiment. So this right here is the molarity of the actual acid in our stomachs. The reason why this guy is here is the same reason why the first one was there. This is for unit conversion purposes. So here you've got liters and you have milliliters. No, sorry. The liters are there to cancel liters. Hang on. We actually want to be left with milliliters because we want to know the milliliters of stomach acid that gets neutralized. The second thing that cancels, and this is the other reason why we got to bring in the molarity of our stomach acid, is so that moles of HCl can cancel moles of HCl, so that the units we're left with are milliliters of stomach acid per grams of antacid. So this leaves us with milliliters of stomach acid per gram of antacid. Alrighty, and it is 10, so I'm gonna go ahead and call office hours for tonight. It was non-stop. Great office hours. Thank you everybody for contributing questions. I think this may be the best session we have, and it is the second to last, so one more to go. And then we'll be calling the semester a wrap. So I will catch you all on Wednesday. Lecture and office hours again. Later.